In this video, we'll explore activation functions, a key concept in deep learning. We'll focus on functions like Tanh, ReLU, and Leaky ReLU, which were developed to address some of the limitations of the sigmoid function. For more on the characteristics and limitations of the sigmoid activation function, please refer to the previous video. The sigmoid function, a commonly used activation function in artificial intelligence, outputs a positive value between 0 and 1 for any input. However, when input values are extremely small or large, the gradient approaches 0, leading to the gradient vanishing problem. To overcome this limitation of the sigmoid function, various other activation functions have been developed. Activation functions can be broadly divided into two main categories: S-shaped functions and non-S-shaped functions. S-shaped functions include the sigmoid and tanh functions, while non-S-shaped functions include ReLU and Leaky ReLU. Of course, there are many other activation functions, but in this video, we'll focus on three: Tanh, ReLU, and Leaky ReLU. Let's first take a look at the Tanh function. As explained in the previous video on the sigmoid function, because the output of the sigmoid function is between 0 and 1, it is always positive. This can lead to issues like gradient vanishing and causes an imbalance in learning since it's not symmetric around 0. The term Tanh stands for hyperbolic tangent, and it can be expressed with the following equation. The Tanh function outputs values between 0 and 1 when the input is positive, and between 0 and -1 when the input is negative. So the entire output range is between -1 and 1. Since Tanh is symmetric around 0, it can make learning faster and more stable. It also has an S-shaped curve similar to the sigmoid function and offers non-linearity and differentiability, making it useful for learning complex relationships. However, because Tanh has a similar shape to sigmoid, when the input values are very large or very small, the output approaches 1 or -1, respectively, and the gradient approaches 0. Therefore, the gradient vanishing problem can still occur. Now let's talk about the ReLU function. In traditional functions like sigmoid and Tanh, as the network layers deepen, the gradient can diminish, resulting in very minimal weight updates. This is known as the gradient vanishing problem. ReLU was developed to alleviate this issue and is defined as follows. To put it simply, any value below 0 is output as 0, while any value above 0 is output as it is. When we take the derivative, the gradient is 0 for negative values and 1 for positive values, which means the gradient is always 1 for positive inputs. This significantly reduces the gradient vanishing problem, even in deep neural networks. To explain further, the ReLU function outputs 0 for negative inputs, which deactivates certain neurons, leading to sparse activation. This sparsity helps reduce the computational load. Let's break down sparse activation. Sparsity refers to a state where most elements are 0 or close to 0, like in word frequency data with a bag of words model or one hot encoded categorical data. In the neural network context, sparse activation means that only a portion of neurons in a layer are activated, with the rest outputting 0. This reduction in active neurons improves computational efficiency. However, a problem called dying ReLU can arise. This happens when some ReLU neurons consistently output 0, which means they no longer contribute to learning, potentially decreasing the model's performance. Next, let's discuss the Leaky ReLU function. Leaky ReLU is a variation of the ReLU activation function, designed to address the dying ReLU problem. It is defined as shown in this equation, where alpha is usually set to 0.01. When differentiated, this means the gradient is 0.01 for negative values and 1 for positive values. By maintaining a small gradient for negative values, as defined by alpha, Leaky ReLU allows neurons to continue learning even when the input is negative. This can contribute to improved performance in deep neural networks. To summarize activation functions, sigmoid, tanh, and ReLU are the most commonly used activation functions. The sigmoid function was widely used in early neural networks and is still useful in the output layer for binary classification. However, it is rarely used in deep learning due to the gradient vanishing problem. The tanh function is an improved version of sigmoid and is mainly used in certain structures like RNN, though it still suffers from the gradient vanishing issue. The ReLU activation function is computationally efficient and alleviates the gradient vanishing problem, making it the most widely used activation function today. It serves as the default activation function in various neural network models, including CNN. Leaky ReLU is a variation of ReLU, primarily used in hidden layers, and is especially useful in deep neural networks where there's a potential for gradient vanishing. Here's a general strategy for using activation functions. To start, use ReLU by default when designing a model. If the model deepens and ReLU's limitations impact performance, try using a ReLU variant like Leaky ReLU. For binary classification problems, use sigmoid in the output layer. And for multi-class classification, use softmax. In RNN-based models, tanh and sigmoid are commonly combined. Since each activation function can perform differently, depending on the data and model, it's important to try various activation functions to achieve optimal performance.